Welcome back to DVCon. Woohoo! Feels so good to be here. All right, great. So good to see so many recognizable faces. We haven't changed all that much over 3 years, so that's good. So for those of you that don't know me, I'm Tom Fitzpatrick. I'm the vice chair of the Portable Stimulus Working Group. So along with Prabhat Gupta from AMD and Mike Chin from Intel, we're going to be talking to you about some user experiences with the Portable Stimulus Standard. We've been working on this for several years. We've done a number of presentations at DVCon about it, and so we wanted to give you an update on kind of what we're working on for the next version, which we've tentatively called 2.1, but at the end of this I'm going to take a poll to see whether or not you think we should call it 3.0. So we'll see how that goes, because there is a lot that we've been working on. So let's go ahead and get started. So the first thing, the biggest change, as you know, from the beginning we've had what we've been calling a DSL, or domain-specific language. This is a new language that we've developed in the committee, and we've also had a C++ library that essentially implemented most of the same semantics as the language. And there was sort of a debate whether or not users would be open to learning yet another new language, even though, as we've talked about in the past and you'll see today, it is important to have a language that is specific to stimulus because it is kind of a declarative domain, and we didn't really have a declarative language for doing that. The C++ equivalent was, even though it was C++, it was sort of like saying somebody who's a generic C++ programmer can just go ahead and write System C, right? It was a library written in C++ to essentially give you a C++ way of specifying the DSL. So it wasn't C++ that would execute on your end platform. It was C++ for defining the model that would then get generated into whatever would run on your platform. So for a number of reasons, not the least of which is that there are a number of things that we've been adding to the DSL that we couldn't actually do in C++. We are getting rid of C++, and it is now just going to be called PSS. So there's no more a DSL, it's just PSS. When somebody says PSS, this is what they're going to be talking about, right? So that's the biggest change. The other big thing that we've been working on is defining coverage. So from the beginning, PS 1.0, we've had coverage similar to the coverage that we have in System Verilog for being able to cover the data space of things. So you could have cover bins of stuff and saying, you know, did I hit every address range or all that kind of stuff. That's been there pretty much from the beginning. But if the whole point of cover points and cover bins and stuff in System Verilog is to figure out what the constraint solver is actually giving you when you constrain transaction level data, if PSS is all about constraining behavioral level stuff, we needed to figure out what does it mean to cover that, right? If you're going to randomly generate stuff, you need to know what you randomly generated to know if you've actually reached your goal. So we've been working on defining behavioral coverage. So kind of given a stream of action executions, we want to be able to find out whether a given temporal scenario actually occurred. So that means we have to be able to define what those things are. So we created this thing called a cover statement, which specifies the interesting scenario. This is the thing that you're going to be looking at. You can kind of think of this as sort of a cover group at the behavioral level. And then a monitor encapsulates the behaviors to be covered. So as we'll see here, we have a couple of actions that we've defined, and we're going to try to see whether or not these things actually happen. So we can create a monitor. We're going to declare these write and read just as if this were an action, kind of, right? So then we have an activity. We're going to do a write followed by a read. So we want to try and see if that happened, right? So in this set of stuff, we've got a write here, followed by a read here, followed by a read here. So either one of these reads could theoretically match this monitor, but we want to be able to be a little more specific about it, so we can create a cover point here that says, okay, we have a read after write, which is the monitor, and then in that activity, we're going to do a read after write with the write address and the read address being the same. So this read has a different address, so this one doesn't count. This is the one we want to count. So this is the match of that sequence of doing the write after read with the matching addresses. And then we also need to be able to specify things a little bit more carefully. We can specify from defining an activity that I want these two things to happen in parallel, right? Which basically means they have the same set of predecessors. When those predecessors are done, they can both start. We couldn't really specify that from a coverage perspective, saying these two things are going to start at the same time, because that's such a weird concept when you actually look at what ultimately gets implemented. So we came up with this overlap idea, which says I'm going to do a write, and then I'm going to do a read that overlaps with another write. So as long as this write either starts or ends somewhere in between this read here, that counts. So if these two things were done in parallel from the activity generation standpoint, the overlaps would be the way to detect it. So there are a number of constructs that we created to be able to track these kinds of things. So the first is just defining an action traversal, right? So if you say do A, maybe with some constraint or whatever, so that's the execution of an activity. And then there's concatenation, which says do M1 followed by M2. Once you see M1, you start looking for M2, and when you see M2, you've got the match. There's also an eventually, so it says at some point after I start looking, I'm going to see the M. And then there's a sequence which says M1 followed by M2. You can either use the sequence keyword or just M1, M2 in the brackets. So similar to the sequential statement in an activity, you have the same sort of thing here, so the sequence is implied. So I get an M1, and then sometime later I'm going to get an M2. So if you really want to get into formal semantics, and boy have we ever, it's sort of a concatenation of M1 followed by eventually M2. Right, so as soon as M1 is complete, you start looking for an M2, and it eventually happens. There's also the overlaps that I mentioned. So M2 is going to happen somewhere within M1. And then there's also a select. You can do either M1 or M2. Right? So from these, we can build up a pretty significant set of stuff that we want to look for to see if it happened. Right? So we are still working through all of the nitty-gritty of the semantics of these things. There's some of the syntax is probably going to change and all. But conceptually, this is what we're working on. And this has probably been, I mean, we've been working on a lot of stuff from then, but we've been working on this by itself pretty much for the entire time since the last release. So this is kind of the thing that's gating the next release, because this is something we know is not there yet, and we want to have it. So currently the plan is to figure this out and then see what we can do in terms of an actual release. We think we're pretty close. Can't really commit to anything. We're hoping that we'll be able to get it done in the next month or so, and then we should be on track to have the next release sometime late summer maybe, okay? A few other things. We've added runtime messaging, so both solve time and runtime, right? So as you're having the tool process what you're going to generate, we have a print message and a format, and these do exactly what you would expect them to do. They take a format string and print stuff out or create a string. We have runtime messaging, where we have messages with a verbosity there to Cliff Cummings' Everlasting Horror. We're using the same scheme that UVM uses. And then we also have error and fatal. An error just says there's an error. Fatal will stop everything, and there's a return status value that you can send. It's a great way of keeping track of what's going on. You know, for debugging purposes, if something happened while you're trying to solve, you can see what's going on. You can make sure that it's giving you what you expect, you know, whatever you might want to use messaging for, and you can have verbosity here. So as you're working on it, you can have everything spit out messages, and then you can turn off the verbosity and you won't see it anymore. So that kind of thing. We also have file-based I/O here, so we can either use via handles, so we have create file handles, you can open files, close files, do all the kind of stuff you need for files. And then for simple files, you can read lines and write lines straight to a string file name and give it a list of strings, etc. So this is really helpful for if you're going to be reading data in from something and start using that as a way to help generate the stimulus that you need or whatever, so we have that. You can also use it to dump out your own log file information if you want, that kind of stuff, so pretty helpful stuff. We've also added randomization for lists. So once you have a list here, so in the pre-solve, we're going to actually generate this list. We don't care what the data is initially. The important thing, though, is that this list has a fixed length at this point, and then we can randomize the list. So when this struct here gets randomized, the list is marked ran. So whenever we randomize the struct, just like every other ran field, the list will get randomized. We can't constrain the size of the list. As I said, it's going to be fixed, but we can use the size in a constraint, sort of as a state variable. So it allows us to, if you want to model some of the data that's going to get generated as part of your portable stimulus model, you can use a random list to do that. So you can randomize the data and then pass the list around if that's what you choose to do. We're also adding procedural randomization in the realization layer. So if we have a struct here, S1 has two rand fields A and B. We have a struct S2 which has a rand field of S1 and a constraint that says F1.A is less than F2.A. And then in our action, in our post-solve, which is the realization layer, we can randomize these variables V1 and V2. V1 is an S2 and V2 is just a bit field. Right, so we're going to randomize these two variables, and these are what gets randomized. So when we randomize S2, The F1 field gets randomized, the F2 field does not, because it's not marked as random. So when we randomize S1, we wind up randomizing A and B of here V1, right? And so the constraint that we have in inline constraint says V1.F1.A is less than V2, where V2 is this bit field here. So that's a 4-bit field, so F1.A has to be less than 15, depending on the value that we wind up generating for V2. And then we have another active constraint here that F1A is less than 100, because we've said V1.F2.A to 100, and we're saying that's less, so F1.A is less than 100. Right, so F1.A is going to be less than 100 and less than 15, which means it's going to be less than 15, which means that the value that we generate for that is going to be anywhere from 0 to 14, and B is unconstrained. Right? This is very similar to the randomized statement in System Verilog, but now we get to do it. But the key here is this is in the realization layer, so this is actual procedural code here, but it's done at the PSS level. So we will wind up doing the randomization at the PSS level, give you a value that you can use, and then when it goes and gets generated as the actual code, that's the data that will get used. We've also added a distribution constraint, again, just like System Verilog. So we use the same notation. We have the colon equals to say the weights of everything from 100 to 102 is going to be a 1, 200 is going to be a 2, and 300 is going to be a 5. Or we use the colon/ notation, which says that the set of values from 100 to 102 is going to be a 1, so each of them is a third. This is a 2, and this is a 5. And as in System Verilog, the distribution constraint is, those of you that are fans of Ghostbusters, it's more of a guideline than a rule, right? If the set of values that gets defined through the hard constraints includes the set of values that are in the dist constraint, then the dist gets applied to the set of values that would otherwise get generated. But the dist by itself doesn't constrain the set of values that are going to be generated. We've also added in the ability to use labels here. So we've had labels for a while. It's a way of just sort of organizing your code. But now you can use those to reference action handles, essentially. So when you say do this action here, so you don't have to declare it explicitly because it's an anonymous traversal, but by giving it a label, you can now refer to xfer.size here, which is the size field of this mem-to-mem xfer action. So it's a way of giving you the opportunity to refer to things without having to explicitly declare all of the different handles that you might use. So you can use anonymous traversals if you want and take advantage of the labels to be able to refer to things. Just a couple of little things to make things a little bit easier. Okay, this is another relatively big one. So if I have this situation where I have an action config and an action B, and B inputs a state and config outputs that state, if I have an activity that says do bring up and then do A and do B, what I want to be able to do is to make sure that B happens immediately after A, right? Because that is, given my design and my spec, I need to make sure that I can actually do that. Okay, the problem is that B has a precursor. It needs to have this state variable generated. So previous to this new feature that I'm going to show you, we would infer the config X action to supply the state variable to B, and that could get put in anywhere prior to B starting. Right? So if it goes here, it's in between A and B, and if it's here, there might be other stuff going on. You know, config X could be longer than A, right? So we don't know really what's going on. So we're not achieving our goal of stressing the design by having B immediately after A. So now what we have is in our activity, we want A and B to be stuck together. So we added this atomic statement which says A and B now must happen as a unit. And anything that is a dependency of any of these is a dependency of the entire block. So now I can only do config before I even do A, so that A and B will happen immediately. So now I've reached my stress goal. So I'm always going to infer that action prior to the block, and this is how I can make sure that I'm going to do these, because A isn't going to start until everything has been done, right? And then the other thing we've added, again, in the realization layer is a way of doing a concise read, modify, write. So in a single statement, you can do a read, modify, write instead of having to do it explicitly. So we've added write mask, write val masked, write field, and you basically do it exactly as you would expect it to, right? So you specify the field here and then what the values are going to be. So you're only going to write these bits of this. And you can also do the write fields directly where you specify the name of the fields and the set of values that are going to be written. And then we have some additional new features which I didn't think were really necessary to have slides on. So we have static functions in components. This is just something that will, so you can use the double colon operator. So if you have static components, you can have static functions in them. We've added tag and address value. So these are useful ways of being able to refer to sections of memory as elements that you can use in programming. We've defined a base type for enums. And we're adding floating point computation and storage types. So we're going to be supporting floating point types as well. And the reason I don't have a slide on that is because I don't understand floating point. So I leave that to Matthew. All right, so those are the new features. I'm now going to hand it off to Prabhat from AMD. He's going to talk about how they've been using portable stimulus. And then Mike from Intel is going to talk about their experiences. Then we're going to bring it back. We'll have a panel discussion. So there are a number of members of the committee that are here. So Prabhat.
So I'm Prabhat. I'm actually part of the Accellera committee, and we contribute a lot in the PSS language world, and a user also. So this is from a user point of view. I'll be introducing the project that we worked on for this presentation and describing our initial approach of PSS implementation for this particular project. And then how we morph that into what I call a first-class model, or maybe PSS 2.0 model for us. And then describing constraints. We learned a lot about using constraints. As you probably all know, constraints are a big part of PSS language, how you model the test space in PSS. And so I'll be describing with that. And then something about PSS methodology, probably for within the company or across the industry. And then a conclusion. But I must say that we had a lot of fun doing this project. It's really fun to create new tests, and the way the portability and the value of portability and expressiveness of PSS comes out to a person who's using it is amazing. We had a lot of fun. Okay, this was the project. It was a IP for AI applications. It's a grid of compute engines and some memory tiles and DMA tiles, which we call shim tiles. The project was to do some verification of this IP. A lot of this information is available on the link publicly. This product, an x86 processor with this IP, was announced by our CEO, Lisa, at the last Consumer Electronics Show last January. So that's available. This particular IP, the AI array, is a set of compute engines that's highly connected. And then you have what we call memory tiles that contains a lot of data for the compute engines. And then the shim tiles do DMA from very high-speed DMA from system memory. And this whole subsystem contains an embedded processor that in production mode runs a production firmware, where a host processor, in this case x86, part of the SoC, will submit work to the control processor, which will send the work or compute kernels to the compute engines. And the goal is to verify this subsystem, not necessarily just the IP, for functional performance and post-silicon validation, which we did all of those in this project. The focus of this presentation is what we call circuit switch DMAs. So from the previous slide, the grid that we had, there are actually more than one physical channels going east-west and north-south. And you can do DMAs from any of those tiles to any of those tiles. And by circuit switch, meaning you have to actually configure the circuit before you start the DMA. All of these DMAs are kind of streaming, where you have to start at both ends for the DMA to work after you set up the circuit. The whole grid can be partitioned into multiple columns. This is for an application, maybe at OS, multiple applications using this IP at the same time. We call them partition isolation groups. And usually adjacent columns are isolated together as one group. And when you're creating the circuits, obviously they can be cyclic and they can cross an isolation boundary. So this is what the focus of this use case is. This is the bigger environment. We have this AI array, the grid on the top, and then a kind of another processor subsystem with its own address translation and a network, and some standard communication mechanism for control network, and a high-speed connection to the memory subsystem, and then some registers for the AI block. Let's go through what were the different test bench environments. So we started with the IP level, and there is a little bit of history here. We got this IP from our what we call AECG team, formerly Xilinx. I guess some of folks are here from that team in the back. Thank you guys for your help. So this IP came before AMD and Xilinx became one company to this subsystem team. And this environment is from the subsystem team perspective. They got the IP and they integrated within their environment, replaced the UVCs with the UVC the subsystem team had, same bus, and then ran some of the UVM sequences directly that came from the IP team at AECG. So our first environment was to take this environment that is part of the subsystem and convert some of those tests to PSS. That's why the PSS is now driving UVC, driving the array in this IP-centric environment. And now we have this complete subsystem where you have the processor, and the goal was to now run the same test, but it's running on the embedded processor. In this particular case, in fact, the PSS code is driving the embedded processor as well as some UVC that's connected here for configuring and powering up and doing reset kind of thing. So it's a fairly complex environment even at the subsystem. And the next environment is full SoC, where you have x86 processors and all the subsystem. And you take the same PSS code and kind of generating two binaries that run on the embedded processor and x86 here. So this is all the environment we worked on, and then eventually we took it to the post-silicon. Actually, in post-silicon, a PSS-based test was the first test that ran during the post-silicon bring-up of this processor, because the DRAM was not up on the day one. And we could load the embedded processor through JTAG. Just the normal, what are the challenges for this environment? For array itself, it's a highly connected array with many combinations of routing, and not just circuit switch, there were packet switch data transfers, among other things. You have to isolate into different groups and then create circuits within that group and route it, and it's just a complex piece of IP to verify. You go to the subsystem, I guess the AI team here, the IP team can attest to that. They do this using UVM currently. Then at subsystem, we have new interfaces, whole processor subsystem. Usually the test will be run through keeping the embedded processor in bypass mode, but running the test on the embedded processor is important for functional and performance region. And you don't have that. You have to manually code some test that will run on the embedded processor. At SoC level, we really want to verify this as part of a multi-IP test where we want maybe an image processor sending something to the AI processor, doing some AI type of work. Like in first slide, we had use case where you could do auto framing in the Microsoft Team meeting or eye gaze detection. And so you really want to test that. And doing that test manually, writing C code or assembly code at SoC level is extremely complex. And we hoped with this particular project that will address some of these issues or challenges. Okay, so our team was not part of that subsystem team. We were outside team helping that team. That was a new team at AMD, and we said, okay, you guys do the work, and we will on the side work on the PSS and show what the value is. So our first goal was to prove that it has value. And we kind of decided that portability will be first goal to quickly show the team. So before we go into that, what a test look like? You usually power up the array, configure it, boot the array. You find some legal isolation group, and then you set up some circuits within those isolation group, and then you do the n number of DMA, and then you repeat this process maybe with a new set of isolation. So that's the typical test for circuit switched DMA testing. So the step one was, well, we had some UVM tests that were using some fixed isolation configuration and kind of procedural code, all those things. So we said, okay, we're going to take that test and convert that to PSS and still drive the same UVCs. So we did that. Once we did that, the immediate value was that we can retarget now that PSS test by flipping a switch, and we generate some C code that runs on the processor. The immediate value we got out of it is that from this processor, you could send register sequences through many of these interfaces. So we could randomize that. We could randomize all the addresses here for the DMAs, even though it was kind of a directed test at the UVM level. You get this additional benefit that you have the test for the embedded processor that you can actually run in post-silicon, and you get some randomization just by doing it in PSS, especially for the embedded processor. So those were first step. It did show a value for portability, but how does this all work? So on the top, this is like that IP environment I was talking about. You have the UVC driving the array, and you want to write PSS test. In PSS 2.0, we introduced a thing called executor, where you can actually define what is the agent that's driving, which could be an embedded processor or a UVC. So you define an executor. In this case, it will be a tool-specific way to specify that it's a UVM executor, but you instantiate that executor. The syntax is omitted here. So you create an executor that's this UVC, and you're going to drive that. And then you define your memory in PSS, again, which was a new thing in PSS 2.0. You can probably go back to the previous year's tutorial for more details or look at the spec. And so once we define those, we have now a way to drive that. And this is the PSS code, exec body or realization code for, say, one of the actions that's configuring the array. And here also we are using standard PSS to write registers, which we have defined here, register and memory, or write memory. So this particular code is portable because we have these PSS procedural language to write memory and registers. And then these standard write32 or write value function, they get kind of tied into the UVC sequence that can do the exact same thing through some tool-specific integration. Now we go to the subsystem. Now this integration PSS file changes, and you now, instead of specifying a UVM executor, you specify an embedded processor as well as a UVM executor for this subsystem. And your memory mapping changes, your register mapping changes, and you kind of describe that in here. So you're, again, the same action. Maybe this was the boot action, booting the array, same action, same writing, same register, same memory. And you tell the tool, now you're actually generating for this processor code. So this is the C code. This is the typo. C doesn't have exec body. This code will get converted to kind of just some pointer dereferences, and now you're ready to run the test on the embedded processor instead of driving here. You take this same environment to SoC. Here you do need to generate two binaries, one for x86, one for embedded core. The test remains kind of same or reusing the same sequences in PSS that were driven here. The important thing is that in this case, we have two separate cores. They're kind of synchronizing. So you could say something like, hey, x86, go power up the array, and hey, embedded processor, run some DMA. And in PSS, you exactly write the same code that I described. Do this, do this. And they're happening on different processors. How they are synchronizing, it's all under the hood. It's pretty fun to write a code like this, and you generate two source code, one running here and one running here. It's pretty amazing to see that once the initial integration is done, and fun, actually. Okay, so we had our first model. We showed that we can go from kind of IP subsystem to SoC, and it shows the portability value of PSS. But I guess in our mind, at least in the PSS committee, the portability is a secondary value that we get. It's more of how you express your test. The construct that allow you to, at very high level model, your test space is more important. So this is what we started to do after our first model, that, okay, now we need to really make use of PSS, and that's the model we are going to make. And in PSS board, we call our code a PSS model, not the test. Usually, the test is the top level action that eventually you use to create the test. And rest of it is PSS model with attributes and whatnot. Okay, so what did we want for this model? For the circuit switch to DMA, we wanted to set up random legal isolation groups. We wanted to set up multiple acyclic circuits within all the isolation groups. We wanted to have then multiple parallel DMAs going across different isolation group and then have automatic data checks. And a simple enough API that somebody sitting in a lab just quickly creating a couple of tests. So that's the highest level of the API we wanted. Some of the example tests run n parallel DMAs with random circuits in random isolation setup. So that's like completely random thing. Imagine writing that by hand, C code running on that embedded processor, extremely complex. That's a single-threaded processor, by the way. You want to maximize maybe DMAs to system memory for your SoC level performance testing. Maybe in post-silicon, you want to validate every single path at early bring-up to build confidence that this hardware is okay. So we wanted our test to look something like this. And when I mean something like this is the exact test. That's it. In this one, you're saying that, hey, do the DMAs, but make only one isolation group, meaning a whole array is participating in that DMA. Or you just want to randomize everything. And again, this all works in UVM as well as on the embedded processor. This is a standard diagram for a PSS model where it's kind of following your RTL hierarchy. This is not RTL code, this is PSS code. A component is modeling compute engine and memory tile and shim tile. And then you have in PSS world, you have describing your memory, your resource pool, which usually represents a DMA channel, your buffers. In PSS, if you know, buffers are used for scheduling things, producer-consumer type of relationship, and you need to have pools. Stream pools, again, another kind of scheduling construct in PSS, allowing concurrent running of actions. And your initialization of memory and stuff. And then we created these top-level kind of API actions for doing the DMA, which you can use to build up other tests. How did that look? We had a base component with actions for configuring for that particular tile isolation, configuring the switch at that tile, and then to start a DMA, these were streaming DMAs, so you have to start the DMA at both ends. So you could either do stream to mem or mem to stream. So this is a very high-level abstract action. And then we had the concrete component for the tiles. The point here is that these abstract actions allow us to write tests at a high level without worrying about the next project. Actually, we could use all those actions in our next project, which we are doing right now. It's a good way to design your PSS model to separate your base abstract actions into its own file. And PSS aspect-oriented thing allows you to extend or override, which I guess Mike will talk more about, and cleanly separate the base functionality with the rest of the SoC or project-specific things. So like I said, this is a complete test, whether it's running at the IP UVM level or that subsystem with embedded processor or at the whole SoC. This is the complete test. It's saying do the parallel DMA. I don't care how many well, I do care in this case. There's only one isolation group, and that means the whole array is one thing. And rest of things are random. This is the really fun of it. Once you have that API, the tests are really simple no matter what level of abstraction or vertical integration you are. So this test graphically in a kind of UML activity diagram looks like this. You have this action that takes a state object. Again, state is a PSS construct allowing you to model states, state machines. So this is the state of the isolation, and this is state of the circuit within that isolation, and it takes that state objects and does the DMA, which the PSS tool takes, solves, and creates the final test. All these green actions are inferred. So the tool knew that to do this, I needed to set up isolation actions. I needed to write some data somewhere before I can do the DMA. I needed to set up the circuit based on the isolation setup and do the DMA at the source and destination and check the data. I guess check data could be part of this. And these things are at the same level, meaning they're doing in parallel, and the stream construct in the PSS allows you to model that these should happen in the parallel. Okay, so while we were doing this, what we call Model 2.0, we had to think about the API a lot. Designing those abstract actions that were in the previous slide as well as a level above was a long process. And the constraint actually played a major role in how we define those. And I'll talk more about constraints later. So you come from the procedural world usually, and you think about, I'll do this thing and then do this other thing. And that's how we started thinking about it. So we had this kind of a base action saying this is our API, and there is a story on the parallel thing too, which you hold on, why we made it parallel. But the idea is that we'll have an action compute-to-compute kind of DMA, and it's going to input a circuit state, create some new circuits, and do the DMA on that and output that circuit, meaning now you have a new set of circuits. So we did that. The problem with that approach was in PSS, the action and what I was inferred is one big constraint solving problem. And even with this example where we had, I don't know, like 4 compute row or something, and not a very big array, but all the ways the circuits can be configured or isolation can be configured meant that it is already a huge constraint solving space. It's the constraints always making one global constraint solving problem usually, unless you go into activity, and solving it for you. When you have this kind of procedural thinking that you take something in, you do something, and then you produce something, it usually means you're taking this big circuit state, which already had a lot of rules about how legal circuits work. You're changing something using constraints. Again, here everything is constrained, not a procedural code. Meaning you're writing rules that will be combined with all other rules in the system, and you're outputting a new thing. So doing then this action in parallel, meaning even in sequence, creates a lot bigger constraint problem than sometimes the tool can handle. So you have to be really cognizant of this. And so this was our first write, kind of worked, but it wasn't very fast. So what we come up with is that, okay, since this is a global constraint problem, we're going to solve for everything that we need in our test, meaning all the isolation profile circuits within that one time. And we thought a lot about it. Is it the right thing to do? But it seems like that is the thing. You want to do DMAs in different modes, and that's enough. You don't want to do this procedural, do this, and create new thing, then do this. Usually that's not your goal. So thinking through what really matters and how that fits in a global constraint problem is extremely important in PSS. The power of PSS comes from that constraint solving, but you need to be careful. So we kind of added all the rules in one place, and we had this action where it will just input this state, meaning everything is already set up, everything is already solved, circuits are programmed, and you're just doing pick some DMAs from there, some circuits, and do the DMA. And that helped a lot with the overall process. This is a good design in this particular case. Tip again, if you have a bigger state, see if you can solve that once and then use that and have a clean break and do the next thing. I guess in maybe PSS 3.0 will have something for things like solve barrier. Maybe that will help with this process. But this is an important point, I guess. Doing this process, we kind of came up with how we should approach any new project, which is how we should design our PSS API. And the key really is have that abstract code, which may not be a lot, but do very quick iteration and write all your constraint rules at a very high level. And that will give you a good feel for what works for your system. And generally, designing an API in 3-level process is a good approach. So you kind of encapsulate at level 1 your sub-IP or the lowest level IP, maybe all the programming sequences for that IP. registers, everything encapsulate that, and which is what we did for this, where we had this mem to stream and stream to mem, which were really hidden from the actual test writer. And then your level 2 is the main test writer interface, that action, the DMA parallel action, and that will use your level 1 action. So you got nice encapsulation here. And then eventually you want to have simple API where maybe somebody sitting in the lab, they can just configure some things and get what they want right there in the lab when they're doing the bring up. So that's how we are thinking about designing for projects, PSS API. Okay, constraints, they are powerful and dangerous. Even with a small verification space, you can create constraints that are very hard to solve. So we need to talk about that. Constraints are the backbone of PSS model. That's where a lot of power comes from. Usually the tool will use constraints for action inferences, flow object, which is the buffer stream objects. A lot of time in PSS, you don't have to say that output of this action goes to input of this action. Tools can infer this, which is very powerful when you're doing exploration or designing your test space. The tool will infer that for you. It will infer, I guess, actions based on state dependencies and resource rules. So the point is constraints are everywhere. And usually it's a global constraint solving problem. The procedural randomization that Tom described earlier, I'm actually very excited about that. It will allow me to partition my constraint solving problem where maybe I have some local randomization that I need to do, which doesn't really affect the rest of the system. For example, I'm drawing some triangles on a graphics processor. Number of triangles and the shape of the triangles is not affecting the rest of the problem. So why do I want to add that 1,000 triangle randomization to the global constraint solving problem? So that should help a lot. Some tips. In PSS, you're really thinking about test space, and which is a very good thing in my mind. So you're thinking really hard about what is it that's important, and the tool will enforce it too, because if you write bad constraints or expose a lot of attributes that you want to randomize, it'll be a difficult problem to solve. So you're really thinking about what's important at different level, and you're exposing that to your users who are using that model. So try to really think hard about what is important for the next level and only expose that. Maybe create another level of action that's just exposing that. Another important point is we tend to, in C or UVM, just write rand int. But what you really meant was rand int within this domain. So restricting your domain of variable like this is extremely important. Let's talk about a problem we faced in the constraint domain. So like I talked before, we needed to create random isolation groups. And the isolations group legal, where that adjacent columns can be isolated into groups. So 0, 1, 2 in one group, 3 in one group, or all of them in one group, or 0, 1 in one group, 2, 3 in one group. And these are the examples of the groups you can have. So before we go to the solution, here is a slide about the search space for the constraints. So let's say I like mangoes. My son likes mangoes a lot, actually. So let's say your problem is you want to get n good baskets of mango from m baskets. And let's say you have a row of those. And in your problem, it's not important which number of basket number 2 is bad or not. It's just not important for you. And so you need to find, from m, you need to find some like 3 or 4, whatever, n number of. So this is how one way to write that action. Eat good mangoes, that's your action. And these are the attributes of the action. This is what's making the constraint search space. So you have max number of baskets. You want to say how many you want, good baskets. This is n. And I keep forgetting my own code the next day, so. So this is saying which baskets are good baskets from this array. So basically a bit for each in this array corresponding. And then you want to just say, I want n from the max basket. So this is one way to represent the attributes of your problem space. And this also makes the solution space for your constraint solver, because the constraint solver now needs to find, based on whatever other constraints you have, it needs to find the right bits for each of these. Every single bit with two values, 0, 1, is part of the constraint search space. So you multiply all those values and you get the space. This could be pretty large, right? But you could model the same thing this way. You said you had M baskets, and you just say number of good baskets, meaning from that row 0 to this number is the good basket. Your problem was finding just n good one, and you represented that in a lot less bits than here. And this is really important to do. Important that you're describing the domains of your variables, as well as describing that in as fewer bits as possible. So this is just saying that 0 to this number are the good baskets. Okay, so the problem, we had to find isolation groups, the legal isolation groups. One way to represent that solution space is this 2D array, where each row is representing one isolation group. In this particular example, we just have one isolation group, which contains column 0, 1, 2, 3. Could have two isolation group. In that case, we'll have two of these, say 0, 1 here, 2, 3 here. And then this is what I did, very, very bad code, with constraints having nested for each. You don't need to read it. But the point is, when I represented this as a 2D array, I had to do all these complex things, which I can't understand. It worked, but it's a very bad solution in terms of constraint solving. If you represent the same problem differently, where you said now my isolation group is represented as one array, where each element is saying that this is the last element in that group. So this 3 here, meaning you have one isolation group with 0, 1, 2, 3 as your group. If you had, say, 2 here and 3 here, meaning you have two groups with 0, 1, 2 in group 1 and 3 in group 2. This is the same thing, but represented in a very compact fashion. It has a huge difference in the way we solved the scenarios. And this was the code. Compare that to this mess of nested for each constraints. So it's extremely important to think about a very compact representation of your constraint space. This is just another way of showing that you have one group. So in the 2D representation, you had one row valid, and in 1D you have this. Two groups, 0, 1, 2, 3 in a different group, and you represented in this. I had help in creating this from our good friend Matan, who's doing quantum computing now. But the thing is, in constraint solving research, I guess people call this symmetry problem, where this solution can be in any of these rows. And this is just a burden for the constraint solver. So you want to avoid the symmetry of the solution space as much as you can. So conclusion for constraints are extremely important, powerful, use them wisely. Have symmetry-free constraint solution space when possible. Minimize action inferences. So let's say you're designing your API, and your API is doing DMA. And you know that whoever's going to use that DMA always going to get the data from this place. And there's no exception. Then instead of just having one line for DMA and letting the tool infer that action that's going to pull in the data first, just put that action in. Or maybe have two versions of it, one that just puts that action that brings the data in as part of an activity and expose that, and expose the other one too, maybe for somebody. Maybe he wants to do more exploration. But this is very important. Again, this is for constraint. Use explicit binds. So in PSS, you can say write data to memory and then read data to memory, two actions. And if they're using the same buffer type, the PSS tool will kind of bind them usually. So you don't have to write any more line of code. But if you want that code to go to higher level, Well, and that's your intent, that the write data should go to the read data. Well, say that explicitly. It's another line of code, but it'll help a lot at the subsystem or SoC level, where you have multiple IPs and a huge problem. Avoid chaining of complex constraint from an action input to an output. It's not always possible. In some cases, you want that to model state machines, but make sure those constraints are not very complex. So usually you don't want to see an input buffer with a lot of constraint equal to output buffer with something changed. And it's actually not easy to do in PSS. You have to probably explode that constraints into individual. If you want to just change one thing, you have to line by line copy input to the output except that one. So avoid that if possible. That will help a lot. And we already talked about expose the really important test space attributes to the upper level. Not that I'm randomizing some data. You don't want to expose that to higher level. Okay, similar to System, Verilog, and UVM, I think we need a methodology for PSS, a methodology library within the company and preferably across the industry. So this is my call to action. We should create an industry-wide PSS methodology library, almost like UVM, but not at that complexity. What that means is common types. So if you're transferring data using memory, maybe you want to have common buffer types for memory where you can, within the same company, you interoperate easily with different IPs, or if you have third-party IPs, they can easily integrate and you don't have to write like adoption layers. Some of the things that we are finding is virtualization, address translation. These are very important aspects, and they should probably go as part of that methodology library. How do you describe a buffer that can be in virtual address and how that's mapping to your physical address, and then sometime nested virtualization? I would call for us to create those high-level abstract libraries for standard protocols, PCI, CXL, UCI, that works across vendor, and maybe different tool vendors can have their own implementation for those APIs. I'm really calling for us either through Accellera or through some other means to provide a community forum for best practices, maybe publishing that library type and publishing best practices. Lastly, my favorite topic these days, if we're writing a lot of PSS portable sequences, a lot of time those sequences go to production firmware, at least the initialization portions usually, or sometime power transition. If we have it in PSS, why not use them, export them to use in production firmware? And there's some work already going on. PSS does allow an export mechanism, but I guess maybe we need to explore more in the standard as well as through our PSS tool vendors. And this is becoming extremely important. Not just for initialization, maybe you want to have an environment where you want to do all the power transitions. If not a production firmware, maybe a test firmware that goes through all the legal possibilities of power state transition that the firmware team can use as a reference, which is right now a Word document or usually. And this question comes up a lot for our last 4 or 5 years. Well, where do I start? How do I start? Starting at any place where you can start is the best thing to do. Start small and provide immediate value, which could be in terms of portability or which could be expressibility of PSS, that, hey, now writing new test is a frictionless process once you have a little library of PSS actions. So at different environments, a lot of time PSS is really good at bigger subsystem or SoC level with multiple processors, and you have multi-IP tests. You're writing C test, and it's difficult to randomize. So this is usually a very good place to start if you already have some libraries for different IPs in a usable format at the SoC level. Subsystem level, as I showed previously, writing new tests once you have that right level of abstraction and API is really fun. It reduces a lot of boilerplate. It encourages people to create new tests, which in my mind usually find more bugs. Another important thing of PSS is really focuses you to think about your problem domain. not how you're procedurally coding something. What are the attributes? What are the rules of the system? What are the legal things? And you're writing in a very concise format in PSS as constraints or inputs and outputs and of actions. In my mind, this is the biggest leap for verification. It does allow you to have a communication medium directly from the architecture team to your firmware team to your SoC team and IP team. A very concise representation that everybody can use. IP level, usually people say there is no value at IP level compared to UVM. I disagree. Just the expressibility of PSS is, in my mind, a lot bigger benefit than writing procedural code even for the IP level. And there was a presentation in, I think, 22, describing what other benefits you can get at the IP level. And obviously, if the SoC guys are your friend, you can export your programming sequences, which they usually are not, SoC or post-silicon. For the company, it's extremely valuable that you can sell it to your management. Conclusion, a big reduction in your test development cost, especially for SoC and post-silicon world. Reuse programming sequences, reuse even complex power sequencing tests. Use it at a SoC level where you can easily create that from IP sequences. Use it for bring up. You can create extremely simple tests, thousands of them, validate every single path. You can do a check mark. With our new coverage thing, you can generate coverage reports and show it to your management what has been covered in post-silicon. You can reduce manufacturing cost by making the test very efficient with PSS. And creating a lot of tests, actually. Especially at IP level, creating multi-IP type of scenario becomes piece of cake. And then doing tests for functional power performance and actually exporting sequences of firmware, production firmware, becomes a lot easier and frictionless. It's a great communication medium between all the teams. I truly believe in this point, and we are working towards this goal. Post-silicon, at some point in your SoC, you have to do production type of tests like OS-based. But with PSS, you can do 99% of the work where you're building up your post-silicon bring-up for very simple tests to extremely complex tests and generating thousands of them. This is, in my mind, a huge value for the company. Well, I had a lot of fun. It does reduces friction for creating new tests, reduces boilerplate, and it's fun.
My name is Mike Chin. I'm over at Intel, and I've been working with portable stimulus and modeling. Oh gosh, Matthew, you said 2018 was 1.0, so it's now been at least one pandemic and a few years before. So it's been a while. I work in IP validation, and my organization, we do validation content and execution for IP designs. So if you think about little blocks inside of your chipset, things like your USB controller, your PCIe controller, et cetera, that's what we do. And what we've done in the course of so many years is apply portable stimulus and modeling to our test benches and trying to be able to validate all of our designs. So as we get into this today, a lot of the experiences that I want to go and talk through are a reflection of that kind of now 6-year journey that we've been on and where it's taken us and what have we learned along the way. Okay. So as we get into this, I think it's really important to understand first and foremost why we see the need for portable stimulus. At Intel, at any company you're going to find, you have new engineers that are coming in to be able to do validation work. Well, we got to make them productive. And one of the really nice marketable traits of portable stimulus is because we're uplifting and abstracting the operations inside of our IP or our SoC, we have the ability to be able to allow new engineers to be able to be productive early on, right? As they're still ramping into trying to learn about what does this SoC do, what does this IP do, they can already start doing testing. They can already start being productive and trying to execute test lines or trying to create different types of content, because the abstractions of portable stimulus really allow them to be productive and to do so efficiently and quickly. Okay. That was one of the really big goals that we had as we started adopting this approach to test content with modeling. The other hope that we've seen is that as we take people and engineers that are starting in, we want them to grow their expertise. And this is where you have a really high abstraction level with portable stimulus, but there's plenty of depth that is available, right? You have debug depth, you have the depth in just creating a model, the depth in trying to consider and understand all of the different aspects of your different constraints, how actions interrelate with each other. These help to build a depth of knowledge within the IP and also just the whole notion of modeling itself. And so this opportunity of portable stimulus for us presents that opportunity for allowing validation engineers to be able to grow deeper in their knowledge. We start with them trying to run some tests from a model, and then eventually we say, hey, you've done this enough times, why don't you go and actually write a portion of the model yourself? And that helps to grow a depth in their knowledge and essentially graduate from becoming just a regular user to becoming a power user. And a lot of this premise of our validation kind of goes to our third point here. We work at the IP level with many different teams. We work with subsystems, we work with SoCs, and it's not just in pre-silicon validation that we do so, but also in post-silicon and manufacturing. You got a whole ton of people who are trying to do something effective with your IP, or with your design. And if you have a model and approach that allows you to be correct by construction, if whatever inferred actions are needed for your model in order to have a legal test scenario to execute, this can do it for you. Provides a ton of value because the support load drops, right? And it allows and empowers new users to become effective on their own. So we really see over at Intel here that there is a lot of promise towards this direction of portable stimulus because of all of the positive benefits that we see in terms of enabling validation engineers to do their jobs, to be able to get depth into their work and their subject matter, and to be able to do so quickly, right? And that's the goal in order for us to be able to move forward and be able to scale up into the problems that we're going to encounter. That being said, we've been doing this for 6+ years now, right? We see that there is a lot of challenges to the ability for us to scalably model and be able to scalably validate the design. You know, there is no secret here that I've gone to however many DACs and DVCons of the last few years. Everybody's always talking about the pace of innovation and the complexity of design always increases. And it's increasing faster than we have a capability to verify. Our verification resources are not necessarily growing at the same rate as our design. And so there is a growing gap between where design is at in complexity and where we are in the verification space. So how do we effectively shrink that gap? How do we be able to put our hands around that complexity problem? This spider chart you see over here is just one example of the types of problems that I deal with when we're looking at trying to apply modeling and we're trying to apply reuse, right? You're looking at different platforms. You have pre-silicon platforms for simulation, for emulation, different various IPs. All of those have different types of attached devices that can be added in. There's post-silicon platforms just for power-ons and also for manufacturing. But you just look at that simple gamut of platforms that are out there. If you wanted to write one model that could scale across that entire domain, that becomes pretty challenging. Right. Same things here with things like your test bench, your realization layer. There's probably fewer options here, but you look at things like you have your system Verilog, your UVM test bench. I exclusively work in the C, C++ domain. There's different things that we need to be able to support, and combine that with our platform problem of how do we do this with different types of devices that we need to program up. Lots of complexity that grows. And you look at this from project over project reuse and the amount of features and enhancements that can be added into not just at an IP block, but you take it from the IP to the SoC and also to the subsystem, and the problem that we're going to face continues to grow. So a lot of these challenges are growing every single day. And what can we do? How do we approach this? Because our intent with our content is to be able to try to provide one model as best as we possibly can. But how do we scale that model in order to be able to attack all these different vectors? That's the challenge that we're trying to talk about today. So our modeling problem, I don't have any real action code, unlike Prabhat was kind enough to share some of that with us. But what I wanted to do is give a simple example for you to consider as we talk through these approaches. Just a simple state machine. It has 3 states. It's either on or ready or off. There's a couple of different actions in here that allow us to power on the IP, send some data, initialize the controller, and that's all nicely written out in 26 lines of portable stimulus. No realization layer, just the modeling guts itself. But as simple as this is, if we wanted to extend the capabilities of this, we have challenges. How do we extend this for new functionality? How do we target different platforms that we may want to execute on? I want to talk through the concept of extending our models and overriding. And these are really powerful mechanisms within portable stimulus that allow us to do our jobs and be able to scale well with the problems that we encounter. All right. So first, as we go into this, let's just talk about that notion of what is an extend, an override, how does this relate? Think of this in terms of a couple different areas. One, we have a base model, pretty standard type of logic here. You have one core model that you're trying to implement. It has its basic actions, it has its basic resource pooling, streams, states, buffers. These are all core parts of the model that we need to have. And from us, in our standpoint of, say, project over project reuse, these are things that persist from one project to another. So we don't have to ever worry about them ever going away, right? Our scalability here, what we want to be able to do is address different types of execution platforms, model configurations, and use cases, but you don't really want to put those back into your base model. And the reason why I say that is because when you put it back into your base model, as things change, it becomes a problem when you're trying to scale to the new change. I was talking with another engineer last week, and one of the problems that I was saying was we have to be modular in how we design our code. And the example I gave was that if we do it wrong, it's like trying to do separation surgery for conjoined twins, because you got to figure out exactly what to cut and where, because if you do it wrong, it's going to be a really big mistake, right? So if we design it up front to be accurate, to be exact, and to have a really good, what we call role and responsibility within our base model, it's not going to take a team of engineers to go and flesh this apart and modularize the design, right? So a lot of care from our perspective is taken up front to make sure that we've actually done the right things and made the right choices in order to separate out from what is belonging to a base model of our design, and then what becomes the scalable portion. Okay. That scalable portion, how did we approach it? It became a question of what are the best practices that we have in software that we can apply. My team, myself, we have a heavy background in software, also a very good background in hardware, but we're really well versed in things like object-oriented design, programming. And so we looked at what is it that we do within portable stimulus? How do we apply essentially some OO concepts to this problem? Because if we can do it well, we know in software world that you can apply object-oriented programming and it works well. Can we do the same thing with our hardware design and with our modeling here? So two approaches that we've used to try to extend the analogy. One is to use the notion of extending models. Any new capabilities that we need to support, we want to use the extend constructs within the language to be able to add to the model. So you can compile your base model, you can add additional files that extend capabilities, and then you can have essentially a new model that has the base model plus all of your new extensions. Other mechanism that we looked at was how do we override? And overrides are really, I think, really powerful as well. Because we can have a setting or we can have some model constraints, but if we can override these values, now we can go from supporting, say, 2 DMA channels in our IP to now 8 or 10, right? Maybe there are 2 instances of a finite state machine, but now we want to be able to support 4 or 6 or 8. So having that scalability by overriding the settings and the configuration of the IP is really important because it allows us to be able to do work with just a little bit of a change. So let's go through in the next couple slides here, just talk about these 2 concepts. What did we do? What do we want to get out of this? And then we'll come back to looking at some of the challenges that we still see. So first up is the extend construct. We use this extensively to be able to support new capabilities. Things that we see that are added in from a new project may not have a persistent life cycle past that project or past a couple of projects, but we need to get it supported in, right? So these are optional features, new enhancements that we might see. We also see that this is really good construct when we want to use this for, say, SoC programming or subsystem modeling as well. Prabhat had talked about cross-IPs interactions before, and one of the ways that we thought was a good way to solve this was by using this extend mechanism. I have IP1, a component for IP1 over here, I have a component for IP2. I can have a subsystem model that extends both the first and the second IP to create additional actions, to create additional types of support that are needed that are valid at the subsystem level, right? Take that analogy, apply it to the SoC. For SoC level operations, we've applied this and looked at things like power management. How do we do system power management with a whole bunch of IPs that we've all culled together into an SoC model? And this notion of extending the models in order to support these types of larger actions is really, really useful, and we can do these with very little cost. That's a big key to us here. So how we go about this, adding in new actions, adding in new enums and struct members, resources. You can see here on the slides. What we've done, we have our finite state machine. We wanted to add a new state. Maybe here what we want to do is, originally we could only support reading from our IP. But now this new rev of the project, we can now write to it, but it is not an instantaneous write. It takes a few microseconds for that write to occur. So we're going to add a new FSM state called busy. In addition to that, we have our action that we want to add for writing to the operation, and we want to add another action in order to pull for the completion of that. So just with this simple set of code here and 13 lines of modeling that we can do, it's pretty simple for us to add that new functionality of what does this model support. We can now support new state machine state and transitions. and do so without having to modify the original model, right? This original model that we have still stays the same. We can still use this. It's just that it's extended now to support all of our new capabilities. So the extend construct is really, really powerful for us. When we look at things like optional features of an IP and different types of enables that we might do from one project to another, these all come in and we naturally start thinking about them as, can we just add an extend construct to it and then layer on to the model itself to grow to the next project, okay? The next construct that we want to look at here is the override construct. So configurable parameters for the base model. This is something that we want to make sure that we can set on a project by project basis. So things like sub-device instances, number of agents that you might be having in a particular IP or an SoC, different targets that you might have for memory or different types of resource targets. These are all things that we feel kind of belong in this category of an override. And it allows us to go ahead and set on a per project basis what we want to do. And the other thing that we've found that is really useful with an override is that we looked at the realization layers. And you may have a realization layer, and we mentioned very early on, we have oodles of platforms that we support. But as you try to scale from one to another, there might be some common code for how you go about doing an operation. And as you can see in the example code here, for our basic IP, we just modeled the power down sequence. Well, for this, we want to have this call some IP power down function. At the same time, when we go into a platform that perhaps has more visibility or more controllability and more knobs available to us, if we want to scale this, right, we still have this core operation of a power down that's supported. But now instead of just having that power down, we may also have additional things that we can do, maybe in our pre-silicon platforms, where we can shut off some clocks. We need to do the power down sequence itself. And we can also do some verification. Maybe there's some RTL signal visibility that we have, or some other sorts of visibility metrics that we can measure. So having this ability for us to override the action of a power down is very powerful, because now what we can do is supersede the original intent, do the actual work that we can support on a platform, and in addition, also utilize some inheritance here to be able to use what was originally there. So very powerful construct for us as we looked at looking at FPGAs, which we execute on, or emulation platforms that we run on. You know, the visibility of the platform, the controllability of the platform changes from one to another. And this has been a very core tenet of us being able to reliably and scalably model without having to rewrite an entire model or having a project and platform specific model. This allows us to scale. As we've gone through this, though, we see that there are challenges to extending and overriding models. These being the key tenets for us in how we do modeling come not just without any issues. There are some problems that we've encountered. One of the big ones is, as mentioned in the last slide, you looked at a simple example of a realization layer. But as you need to scale your support to support all sorts of different platforms, the scope of your model changes from an IP model to an SoC, from different types of platforms and the types of, say, traffic generators or attached devices that may be present. All of these create lots of permutations in the realization layer for exactly how you want to do things. Not only that, but sometimes it depends on the tooling that you're using. Your different use cases may present different challenges for you. I may want to use vendor tools to do the bulk of my testing in pre-silicon. In post-silicon, I might make a choice that I really want just a ton of randomized content. Can I use a portable stimulus model to be able to do so? Answer, we hope, is a yes. If I wanted to use AI capabilities in pre or post silicon, is there a way for me to redo my realization layers to be AI friendly, to say give hints that go back into my reinforcement loop, or being able to just be able to be reprogrammable by the AI when it's trying to generate the test itself? That's another use case and another challenge. We've seen that trying to do the realization layers as we scale, it is a sometimes unmanageable problem, but it's something that has to be very, very carefully managed in order for us to be able to deal with it within a finite resource set. And I think as we look at these constructs of extend and override, I think there's a natural question that comes back to all of this. And that natural question for us is, you've extended your model, you've overridden these settings, but is there anything that actually belongs back in the base model? And I think that's a good active question, and one that we always wrestle with and consider as well. We need to be able to use these mechanisms to be able to extend our capabilities into where we want to go into the future and what our job role is for validation. But it is also important for us to understand and recognize that some of these capabilities that we've added now become core pieces of the model that we need. And so we actively have these decision points where we also need to think about, after we've extended, do we roll this back into the model itself? Okay. I can't really tell you guys what the criteria should be or what's the decision point where you have to decide this, but my encouragement in this is that we don't just take these constructs and say that's all we're going to do. We also need to be thinking about, in totality, whether what we have within the base model, within our extended portion of our model, within our overridden configuration settings and realization layers, does that fit? And it's a constant kind of refactoring question that we've asked and we've grappled with over time. We've found different decision points that are key for us. Like if we see some capability that is going to be present for 2 generations or 3 generations, then okay, that's something that's going to be rolled back into our base model. Right? If we see that the direction of a particular IP is to scale into more instances of a particular subdevice, now let's set our minimum threshold differently. So it becomes an active exercise for us, but I think it is also one that allows us to make a better decision and have a better core model as we look to project over project or different types of reuse that we try to do. Lastly, I just want to go through a couple of other things that we've found to be challenging for us as we've gone through modeling. Modeling capabilities, we've struggled a bit here. Dynamic hardware problems pose a challenge for us to model in a scalable way. Think of things like if you have any amount of dynamic bandwidth calculation, or you need to throttle your actions based off of what the hardware can support. We see that portable stimulus can be very inherently greedy towards parallelizing the actions that it's trying to perform. That may not always be advisable because you may run into a dynamic limit based on how many actions are running at a given time and what the throughput of that model can support. That has been a big challenge for us as we've tried to solve it. We'd love to be able to solve it in portable stimulus, but we haven't found that that's necessarily the best or the most available option today. Another challenge that we've seen in our modeling approach, reconfigurable transport layers. We like to look at things not from perspective of individual agents, perhaps, or individual IDs of subdevices, but sometimes you want to group and you want to categorize different agents or different subdevices. That can be a challenge to model at times. We've had one model with 2 or 3 different types of categories of agents in that model, and trying to model that portable stimulus has been a challenge because you want to express, I have group A going to group B or group A going to group C. Just write a test that does all of that for us. How do we encapsulate that modeling for us and be able to do it in a scalable way has been a challenge for us in what we've done. Vendor and use case specialization, I think, is another big challenge that we've seen. It has been a challenge for us to work in 2 different languages, so it's good that the C++ is going away and we're going to stick with the DSL. That being said, language support for vendor tool capabilities, I think, is one potential challenge that we're going to see in the future. We all know what the different vendors are out there that support portable stimulus. They all have their own capabilities within their own tools and their own specializations. I'd like to be able to drop additional hints to vendor A or vendor B, or even to my internal tool, to be able to have it support more than just what the portable stimulus syntax provides me. There might be some additional knowledge that is only specific to a particular tool or vendor, but I don't have a standard way of specifying that information. And that is a challenge, because now we have to look at how do we manage the problem of multiple vendors. Scalable subsystem and SoC support. I've done a lot with my team on IPs, and we're able to model different IP problems and do so very, very well. But as we look at expanding past the IP into the subsystem, you start combining 2, 3, 4 different IP blocks together. And now you want to make them all work together, either in some sort of synchronized fashion or just randomized operations. How do you do so? What's the best way to link everything together? How do we scale here? We've used the extend constructs to some great success, but I think there are still some challenges that we see when we look at some subsystem modeling or SoC level modeling, because there are some problems that we'll encounter when we try to combine these IPs together. Lastly, I want to look at input collateral for the model configuration. This is coming up in 2.1, but it has been an issue for us in the past. You have a portable stimulus model, but in addition to that, every platform has its own, say, configuration, some other settings. Do I need to write a script to take a CSV file and port it into my model in some PSS-friendly fashion? Or can I just parse that CSV file itself? That's been a very, very big scalability challenge for us as well, because you really want to be able to take the input files, parse them as part of the model, not have to go about doing workarounds to make that model solution work. So hopefully with the new file I/O capabilities, that's going to be a very big help for us as we look forward. So in summary, we believe that portable stimulus works for us. We've done this at the IP level. We look at all of these different aspects of scalability. In order to address them, we look at how do we model in a scalable fashion. And the constructs that we've used, extending the models, overriding settings, has been very helpful for us in it being able to address the challenges that we have here. And as we look ahead, I think that will continue to help us to address the challenges that we see. We'll evolve ourselves as we go through the upcoming projects. But these constructs, they've worked very well for us, and I believe it can work very well for all of you guys as well.
First of all, I will ask each panelist to introduce himself. So
I'm going to go first, because nobody goes first. Yeah. So. I'm Prabhat. I'm part of a methodology group at AMD. We do emulation methodology for the company, or basically our charter is to do anything to help shifting left And that includes emulation, virtual platforms, and now PSS, among other things. And I'm just part of that group currently working on PSS methodology.
Go ahead.
Hillel Miller, I work for Synopsys. Really enjoyed the presentations today from Michael and Prabhat. We'd like to see more and more of those kind of presentations. And as you can hear, PSS is fun. So let's do some more initiatives and hear about them.
All right, I'm Matthew Ballance. I'm with AMD these days, but I started off at Mentor Siemens working very closely with a PSS standard. Now I'm over at AMD working on deployment of PSS along with Prabhat.
Hi, I'm Adnan Hamid. I'm founder and CTO at Brecker. We started solving this system verification problem back in 2008. PSS comes along, and of course we hopped on it, so we're one of your vendors.
All right, and you guys know Mike, and you know me, so. All right, so the first question, if I can summarize it, was in UVM and simulation layer, we can do simulation, we do randomization as part of the simulation. If we want to generate code for post-silicon, how do we handle the randomization? And the answer is that's sort of why we do the randomization at the scenario level, but I'll let you guys expand on that. So if anybody wants to take that.
Yeah, I'll grab that one since I've got the mic. Tom was mentioning the separation between the modeling layer and the test realization layer. And that's actually really important because it gives PSS processing tools the ability to make the right decisions at the right point in time. So when you're going to a platform, let's say that is software driven, where the processor is running at simulation speeds, you don't have much processing power. You can shift the randomization, the decisions that are time consuming, and do that ahead of time on the server. And so what gets put on in your firmware that runs to generate the test or to run the test is the result of those randomizations. Very efficient, very fast. Likewise, you have the capabilities a tool does to move those calculations over to a fast platform. So that two-layer approach really gives tools a lot of flexibility in shifting where the computation happens depending on the characteristics of the target platform.
So I think we'll all agree with that answer, right? We want to move the randomization to PSS. I think the real issue we have in the industry is we have all these people who are expert in UVM, and they don't want to learn some new language, right? And what I really want to say is, because I see this over and over again, PSS is not that far away from what you can do in System Verilog and UVM. So you redo your UVM sequences in PSS, I think you'll end up in a much happier place. And it has the added benefit that you can hand off those things to the next guy up, right? How many people here are UVM engineers? How many of you hate the fact that anytime anything goes wrong on IP, 6 months after you finish verifying it, they come to you and say, help me debug? Anybody relate to that? Yeah, okay, got one hand out of that. Well, you get to give them your sequence, right? You get to give it to them in PSS and say, here, I know this one works. So if it's not working, you screwed something up. Because they always have screwed something up, right? I mean.
Yeah, the way that I think about it in the most simplistic terms imaginable, right? In a random environment, you have one piece of code and you run the simulator with different seeds and you wind up getting multiple different scenarios that get generated from that, right? What we're doing essentially, if you think about it, is we're doing all that ahead of time and generating all of those individual scenarios. And then when you actually go and generate the code, you're going to run this one or that one or that one or that one, right? So that's how you do it at the post-silicon level, is you pick one of those that was previously generated and just run that. So each one effectively is a directed test, but when you put them all together, you've effectively surveyed the entire random space, right? At the very most simplistic level, that's how I explain it. Go ahead, guys.
I'd like to talk a bit about the randomization of the synchronization. So one of the most important things in PSS and what the tools do is they generate the synchronization. Not only do they generate the random numbers, but they also generate the random synchronization. And you save a lot of time versus UVM, where you have to actually manually code in the synchronization. The tool actually generates the synchronization for you at the UVM layer, And then you can use that synchronization in other places like post-silicon system level.
Was the question also that I have the UVM content at subsystem and then I want to have a SoC processor-based content? And then how do I take advantage of all the randomization where right now I have to manually code the test?
Yeah, so I think the idea is straightforward, but I was more curious about if there is actual example for doing this, because basically I don't want to write, bunch of objective tests. I like to use, as Tom mentioned, a small set of tests that are randomized and generate all these formula combination for post-silicon validation. So the idea is straightforward. I think it's sort of useful, but I was wondering if there is actual example of success story or best practice for that scenario.
So the problem of I do have UVM, a lot of extensive UVM content, and I want to just port it to a SoC and take advantage of the randomization and all of the other capabilities that, well, rewrite your stimulus in PSS, including your programming sequence. So that's the simplest answer, and it's going to take a lot of time to rewrite. But one other thing from my presentation was that, well, starting the PSS implementation at any level is good. So that could mean that you write the PSS model like Mike was describing, a simple abstract model that randomizes the key aspect of your SoC or whatever attributes, and you're really thinking about that test space. Then you write actions, and some of those actions, maybe you have to implement C code for that based on your UVM library that you already have. So it's kind of a middle way, and depends on how much work you want to do in porting some of those lower level actions, the more benefit you will get. So there is no way around it, I guess.
Can I just say
Can
one
you go
more?
to the microphone, please? You want to say something?
Just one more important topic on the. So when you generate your test cases in UVM, you actually look and you review the generated test cases. You say these test cases, and you understand the intent. This is what they do. So when you go to post-silicon, you may be regenerating some of the tests. But you will have the knowledge base of what the intent you had generated at the IP level, and you want to see those exact same scenarios in the silicon. You get that level of reuse of the intent.
And I think it's important too. When you get to post-silicon, not only do you want to do whatever you've done in your UVM test bench, but a lot more. Right? So the realization layer is very key in that aspect, because I want to be able to push a lot more of that randomization selection into the post-silicon space. The key problem that I see, though, is when I find a bug from post-silicon testing, how do I take that back? Because that's going to be the real question for us when we need to debug. And having that ability through Portable Stimulus to recreate that scenario and retarget your realization layer is very, very helpful, right? That reproducibility of issues is very, very fast as a result.
Okay, go ahead.
My question related to the how the EDA, the vendor is going to help the IP teams, which we already have a lot of UVM sequences and stuff, right? You guys are going to develop some tools that convert the UVM sequences to PSS. It's kind of, otherwise, like reinventing the whole development is not a right way of doing things.
Right. So that was something we talked about earlier, where it's at the moment it's pretty much vendor dependent on how you're actually going to represent the behaviors from PSS in a UVM environment. If you have a library of UVM sequences that you're using to control your IP, then the calling of those sequences can be the realization of the actions that you want to have, right? And so what you'll get out of a PSS tool would be a virtual sequence that will call your sequence library to do the appropriate things according to the schedule of your PSS model.
Right, right. I'm talking about the virtual sequence conversion, not the sequences. I understand that you can
Right,
call
well,
a UVM sequence from your PSS.
Yeah.
But if I already have a lot of heavy built virtual sequences, are you going to convert them to the PSS? Because that's the main.
Right. So again, that's going to kind of be up to you, and I'll let you guys comment in a second, right? So if you have virtual sequences that represent a behavior of something that you want to have in your system, then that virtual sequence call itself can be the realization of an action in your PSS model. Right? It's when you start trying to combine those at the next level that PSS comes in, because you have each of those things that you currently have represents an action, and you can now create a higher level activity that schedules those actions. Right? If you went to a lot of trouble to create this really complex virtual sequence to do something, you can keep it, but you're also relying on the fact that you're randomizing as you run to get that virtual sequence to do certain things. It may actually be easier to rewrite that virtual sequence in PSS and let PSS do the randomization to take care of that. So it's going to kind of be up to you where you want to draw that line, and I'll let the rest of the guys comment on anything else.
I will comment. I'll go back to the same, where do you draw the line of, should I convert everything to PSS, every single sequence, versus what value I'm getting?
Right.
So, and you need to decide at some point, maybe, at least in my experience, just having simple initialization sequences or power sequences and implement the programming sequences in PSS and take it to the subsystem or SOC and create, just do the proper initialization sequence is a big win for me personally. So I would start there that, okay, I know I can't convert everything to PSS, but maybe start simple. And then whatever Tom said, right, the value is then that you get all the randomization and higher level modeling construct benefit that you can write better tests if you create PSS model and still use some of the UVM sequences.
But do you still believe in conversion from UVM virtual sequence to PSS?
I believe that we should rewrite all the stimulus.
Rewrite, but we don't want to do that one, right? We want the EDA tools to help us out.
There's no magic way. Your general UVM code is not machine readable, really. It's not something that a program can read and then understand the semantics, because you have dynamic objects and all kinds of things going on there, right?
Right.
So there's no, I mean, you're talking about the legacy issue, right? If we move to PSS, we have all this UVM code that we've written, our virtual sequences, our test cases, and you want a way to go to PSS.
Yeah, the other thing is, as you've hopefully seen, it's a lot easier to specify a set of actions than it is to write a UVM virtual sequence, right? So if you have a complex virtual sequence that you've written and you understand what it does, rewriting it in PSS is really not that hard. And so taking that small effort to then be able to take advantage of all the other power that PSS gives you is probably going to be ultimately worth it for you. Now, I understand that you want somebody else to do the work for you, because everybody always wants the EDA vendors to do everything for them.
We are paying for you.
I don't know that that's going to happen very quickly until we get more into AI and things like that, but because of what Hillel pointed out. But I can tell you that as a vendor who also supplies a large IP library, we are looking at providing a PSS interface to the IP that we have as well, which currently is UVM sequences, right? So there's ways to do that going forward. So,
I mean, extending that question, right? Is the PSS is a complete language on it? I see there are still a lot of new construct being developed, like coverage and all this stuff. How do you give confidence for the existing IP people to even move towards the PSS? How do I know that is the PSS is completely covering the whole UVM space or not?
Mm-hmm. Anybody want to take that one, or I can?
Maybe the best, I think it's a great question. And I think maybe the best answer we can provide is being used in production, right? We're writing models that are being ported to all the levels. And is everything there? Probably not, because that's why we're adding things, but much of it is there.
Yeah, I think much of it is there. And looking at some of the constructs that Tom was showing, such as the sequential coverage, behavioral coverage, this is something that, in my opinion, is going beyond what System Verilog UVM offers. So there are actually some differentiators beyond what we've had since 1.0, for example, that truly probably appeal to people purely on the block side. So, yeah, features to be added, but I think right now it's a very capable layer on top of an existing kind of structural UVM environment.
By the way, mentioning coverage again, I forgot to mention earlier, I should have. I wanted to thank on behalf of the committee, Dmitry Korchemny from Synopsys has kind of pioneered and driven the whole behavioral coverage thing, defining the formal semantics and everything. He's done a really great job with that. So much of the work is going to be based on what he's done, and we're just, as I said, we're just sort of kind of fiddling around the edges really at this point. But I wanted to make sure to mention him as well.
So yes, PSS has evolved a lot, and it's still evolving. 2.1 is getting there. I mean, I've seen as Matthew moved from a vendor company to a actual doing the work company.
Hey, wait a minute. Yeah. Well, so is he actually. Sorry.
and interacting with a lot of people, I think. We've seen these new features come in, like randomization and local randomization, distribution, and it seems like it's getting there faster than we ever thought it would be. I mean, PSS, besides the coverage, we have memory as a first-class citizen, and we have registers. I mean, there's not many other languages that have memory and registers built in that work and doing well.
Yeah.
The other point I'll make is if you look at it as a legacy problem, which is very real, okay, that there's a lot of sequences already written up. It's a hard problem, and it goes to what we were just saying, right, that there can be anything in a UVM sequence, so it's hard to port it. But as IPs get more complicated, I think PSS plus UVM is coming up to be a very, very powerful solution.
Mike, good to see you, man.
Yeah, same. It's good to be here in
By
person.
the way, Mike is the man who taught me Verilog back in the early 90s. So he started it all. You blame him.
Well, that's interesting, Tom, because I was going to say you made two throwaway statements here that users don't like to hear when you said vendor specific. So my question has to do with, when you have exec blocks that you're ready to implement in UVM, the language doesn't give you much other than the import, right? But every vendor has a solution layered on top of that. So as a user, we're dealing with vendor A, vendor B, vendor C's solution on how I convert or realize those exec blocks. So is the committee going to address this? I mean, I've been raising this since 2018.
Yeah. So as I mentioned, and hopefully not a throwaway line earlier, the discussion of methodology is kind of up next on the block. So that's where this is really going to come in, I think. So.
I think that's fair, Mike. But I think there's another point to recognize, right, that it's one thing to say we're going to standardize, that's fine. But the variety of ways I see PSS deployed into different environments where it's coming from what the environment needs to be efficient. Think emulation, think post-silicon, think people doing, okay, UVM is a standard. UVM is a standard where I never see two customers use it the same way. Okay. I think I can imagine the constructs, but I still see every place we integrate, we do it custom for that environment.
Right. I mean, the other nice thing about the way PSS is organized is if you do have vendor-specific ways of doing things, those are just different realization layer libraries, if you will, right? So the value that you get from the PSS model, the randomization and all that stuff is still there, and it is relatively easy to go from one to the other. You're not rewriting a whole lot of stuff. You're maybe implementing two different implementations for something, but it's not unlike UVM and C for the same behavior, right? So it's not ideal, but it's easier to manage than it would otherwise be, right?
Yeah, it's not ideal, and having done it with multiple vendors, it's a pain.
Yeah, but it's also a job for you, right? So.
It may not be as big of an issue, at least in our experience. PSS 1.0 didn't even have the concept of executors. They were just up in the air, the action is running somewhere. So we have formalized that. Now there are ways to customize your actions or your low-level function calls per executor or per executor per memory region. There's a lot of things that have been added, and integration, yes, it's a hassle, but I don't know, creating a model is probably a bigger issue here, PSS model.
I mean, as a vendor, one of the hardest things is the procedural code, making sure that when you generate the target code based on procedural code in exec bodies, it's doing the right semantics per LRM. That's not an easy thing. And if all the vendors are going to follow the semantics of the procedural code, then that's even better, right? It's less and less vendor specific.
Right, that's actually part of why we added that, right?
Yeah.
So.
Yeah, so this is a basic question. So let's say I'm doing IP verification and I'm using UVM. What would you say is the biggest benefit of doing the IP verification using PSS layer instead of just doing UVM?
Your friends will be happy at SOC. Or enemies. So to me, I guess I said it in the presentation, is once you define I know UVM can do a lot, and it's been doing a lot for IP level. Obviously, the benefit is SOC or subsystem, where you can retarget it to processor based from normal sequences, right? Just flip a switch. But in my mind, and there was a presentation last year also, that if you have, if you're modeling sparse configuration space and resources, meaning like a DMA channel in your system, the high-level construct of the PSS gives you a much cleaner way, almost like assembly versus writing in C, to express that. And on top of that, when you're writing test, and if you're taking advantage of inference, the test itself looked exactly the same that I was showing, like 4 lines of code. So in my mind, that's a lot better than writing a bunch of procedural code to do the same thing. And if you have multiple interfaces, multiple agents in parallel, just writing code that do this and then do this and not even saying where they're going to run, they just magically run on the right places, big win for me. Just test writing is pretty amazing.
I may be saying the same thing, but the managing of your verification with PSS becomes much easier and much manageable. You basically have a model with which you can generate and see if your intent is satisfied. And as IP is becoming more and more complex with many different configurations, and you need to make sure you've validated or verified your IP for all those different verifications and the cross of those verifications. So being able to manage your content, your intent, I think that is the biggest gain. The abstraction levels, the ability to view a graph that gets generated from a tool, a model, and validate that intent and make sure that the intent goes along throughout the project, that is the biggest gain.
And let me give you a very visceral answer to your question. If your UVM environment is a set of interface VIPs and plus a bunch of sequences, PSS won't bring you very much. But usually, your UVM environment is a bunch of queues, a bunch of control UVCs, a very complicated environment trying to verify some IP, and a lot of that complexity evaporates when you move to PSS. I just said what these guys said in different ways.
Swami, you want to say something? Yeah.
As a quick response to PSS for UVM, I think many people said here, the strongest benefit is probably the higher level semantics that you get with PSS, on the way you get constructs that allow you to get this realization at much higher level. Sometimes it's very hard to do. I mean, we look at UVM as a low-level constraint random programming language or a language, while PSS has got much more higher-level abstracts, right? So certain problem spaces where like state machine modeling or certain graphics modeling, which is natural to do in PSS. It's what you would write in a lot of low-level constraints in UVM, which is really a hell to debug in UVM, you could do it much more efficiently in PSS. I think that's a big, strong, I think they all say in different ways. I'm just saying a practical application. So that's going to be really helpful for you. So.
Cool, thanks, Swami.
Abstraction is good.
Yeah.
I mean, the problem is, I know you probably have experience. You may be overselling it. I'm not sure.
Would I ever oversell anything? Come on.
The thing is, like, I mean, 99% of the DV industry, we haven't really seen the PSS yet. So to really trust something, right, like what you guys are saying, it's very hard. Like, I mean, we don't have enough examples yet in the real scenarios. For example, I'm from the graphics team. I was talking to before. How do we really replace our existing graphics generation with the PSS, right? For example, without any real examples that's there, it's very hard to claim that, okay, this is going to change your life into some heaven or something like that, right? So that's what I'm kind of like, we have to be real careful in what we are actually saying to everybody.
But
Yeah, so
one
you
thing
may, yeah, sure, go ahead, Mike.
One thing I point out to you, you said replace. I wouldn't look at portable stimulus as a replacement for everything, right? Look at it as an augmentation of what you're going to be doing. How can it help to benefit? And I think getting into the experience of doing portable stimulus allows you to get the knowledge, the background, that you can then start seeing how it can apply to you in all sorts of other different scenarios, right? Don't look at it as a wholesale replacement. How do you augment to what you need to do?
Right, yeah.
Right, that's a good point, Mike, if I could. So a couple things. When we set out to develop PSS, we explicitly did not try to replace UVM, right? UVM is actually one of the primary targets for PSS. Right? It may replace some of the sequences that you're going to use, but the rest of the UVM environment and all that still needs to be there because you need some place to be able to run the code that you generate out of PSS, right? So that was never the intent of PSS. The real key was to say, okay, most of, certainly block level, IP level verification is being done in UVM. What we want to be able to do is to take advantage of that and also provide users a way of easily migrating from that up to the SoC level, which is why we split between the abstract and the realization layers. Right? So that was a conscious decision made by the committee to set it up that way and to enable that. So we're not trying to replace UVM. You did also bring up a good point. This is still kind of early. When System Verilog first came out, it took a while for all of the vendors to all support the same subset of System Verilog, right? We're there now, and everybody recognizes System Verilog as being beneficial. It's being used over 80% of the designs that are being done, right? So we expect that ultimately PSS will get there. We're still pretty early in the process, and that's okay. But I will also say, as somebody who has been involved in PSS literally from day one, before it was even officially a working group, we had a proposed working group at Accellera. We started thinking about, is this even a possible good idea? And I can't remember how long ago that was. That was probably 5 or 6 years ago now. When I saw this presentation from Prabhat and Mike, I felt really good about the work that we've done to this point, right? And everybody in the committee agreed, right? I mean, if we could have all patted ourselves on the back over Zoom, we would have, right? The fact that this early in the process, two companies like AMD and Intel are able to be using this on real projects, I think speaks volumes, right? So, there's more work to be done, and just like when UVM started out, right? There was a learning curve. We needed to encourage people to try it. Back then we needed to convince people that constrained random was even a good idea, right? And so we've gotten there. This is just sort of the same thing at the next level, right? We're going to have to continue to work with people, train people, get examples. The more the user community grows and starts using this, the more examples are going to come out. 5 years from now, most of the papers at DVCon are going to either be AI, ML, or PSS, right? Or maybe both, right? So that's how I see it going. That's how many of the members of the committee see it going. But the fact that this presentation was able to be given as evidence of it being used and not as this is what we hope is going to happen, I think is tremendous. So.
I do want to recognize a challenge that I'm very interested in, PSS challenge, next generation graphics, things like Vulkan standard. How do you do the drivers? How do you do the IP? To me, that's a nice challenge for PSS, and I'm really interested in that challenge.
Thanks, guys. Yeah.
Thank you.
I thought I needed more makeup.
Go ahead. Yeah. So I think someone mentioned about taking the fails from the post-silicon to the IP. I think I'm able to relate that if it is the same PSS generated test, we can kind of see to replay that on the IP. But say if it is from a real application, that has nothing to do with PSS in that case, right? So how can we say that we can take that fail directly to the IP with even involving PSS in there? So if we are running a real application and we see a post-silicon fail, how does PSS, maybe I'm missing some nuance there, how is PSS helping to take that back to IP?
Now you go to your scan chain, find all the problems, think about it, recreate the problem in PSS at IP level and debug it. I'm kidding.
That is not a problem we were trying to solve. And there was actually some discussion really early on as to whether or not somebody would use PSS to actually write application code. I never thought that was going to happen. I suppose it's possible, in which case you would be able to do what you're saying, but I don't expect that to happen. But you're really no worse off than you were before either.
but you're better off because you have a lot more test content expressible in PSS at a high level, so you can look at what happened from the real application and say, what does that kind of look like? Here are some PSS actions that might do similar things. Let's see if we can create a test that hits that same failure. If we can then minimize it and bring it back to IP. So you're actually in a lot better shape with PSS.
Yeah, as was pointed out, right? It's a lot easier to create system level test scenarios in PSS. So if you can identify what happened in your application, as Matthew said, right, you can fairly easily recreate that in PSS and then bring it back if you need to. Right?
Yeah, at that point, so are we actually relying on the randomizer to solve some of that, and the PSS randomizer to solve that here? Because sometimes the most critical piece is that figuring out what exactly caused that fail, especially when we are talking about silicon fails, right?
So usually people either blame the software guy or the hardware guy, right? But the way I see it, when you're doing the early bring up, if you have the PSS library, you can create very simple directed test that's covering majority of your IPs. So a lot of hardware paths, because it's easy to create the test. So you basically said, well, the hardware looks kind of okay. And then you go to the next level, maybe during your validation, you're creating more complex tests, multi-IP or mixed with power sequencing, right? And you get the confidence there. So you're kind of ruling out many types of failures. So maybe it'll make, like Matthew said, it'll make it easier to find when you eventually have that OS-based application problem.
Yeah, I think what will be really interesting will be to see somehow to relate the application-based scenarios with the PSS library, right? Because I mean, whenever we generate something from the IP and when we port it to the top, or the SoC and all, that's the content that our randomizer is generating anyways. So sometimes the realistic scenarios will expose, but what we might be missing is actual application point of view.
That's a really good point, and I think that's something we need to think about from the behavioral coverage standpoint. Right? If you're just running application code, is it possible to identify the actions from your PSS model and see if they happened while the application was running? I don't know if we can do that yet, but that's certainly something to think about.
But even if we're not able to, right, you have a very fast platform, you have a very fast means of generating content. Certainly if you find a problem in an application, I wouldn't go to my simulation and try to recreate a test that take me forever, right? But you can play in the post-silicon platform with a portable stimulus model to try to recreate that. And it really is, a combination of what Matthew and Prabhat are saying is you have that efficiency due to portable stimulus, leverage it on the post-silicon side, and then take it back over to your full visibility platform, right?
Yeah, that makes sense.
Okay.
And let me take that same question from a different angle from your side of the world, if I may, right? So if you had an application that failed and you're trying to debug this case, that's one big problem. How many other problems are there around that the application did not hit?
Yeah.
You don't know.
Mhm.
So real life applications, we have to run them, but they're not sufficient for system test. And the real answer to all the questions about, well, I'm using UVM, what do I do? Is there is a serious gap in our verification strategies, validation strategies. We got our IP sorted out. Then we stitch these things together, do a few tests, take the damn thing out, put real software on that, run real applications, and stuff fails, and we spend weeks, if not months, debugging this, right? The software driver guys get screwed up because they're one rev of the spec behind what the UVM guys were doing, or something like this, right? So by being able to fill that gap with PSS, you reduce a lot of these problems, right? Yes, the work has to be done, right? Those models have to be written, but the saving is what you're talking about.
Okay.
Yeah,
Right.
thank you. Actually, one.
Oh, sorry.
So, especially, I mean, when we're talking, I like the idea that these are all generated offline, that we'll be running the PSS, and because it's constrained randomizer again, which most of the DB4s are afraid of to do too many constraints too, right? Because it just stresses out the simulator. So it's good that we are generating them offline, but typically, out of your experience so far, for a most advanced or complex scenario, like how long did that generation time take? Or because there are other tools that are also available which we could do, but they have some overhead, right, in terms of the generation time. So what is the turnaround time that we're talking about here?
I have straight data to share. It is costing roughly 64 cores to keep one post-silicon platform busy. So 64 to 1.
Sorry, 64 to?
64 to 1, right.
Wow.
So we are running 64 cores on generation and compile, so we can download and keep a full-blown platform busy. Now this is a high-end server platform that is taking very big tests, but straight data.
Wow, okay.
Okay. All right.
Constraints are key, so you have to be careful how you model. There is a state of art of solvers, and you can't exceed that. So,
Yeah, you know, back when System Verilog was coming out and all the vendors were comparing their constraint solvers, there was the Einstein problem, right, with all the 5 houses and all that kind of stuff. And we spent probably a year comparing how quickly each solver could solve that particular problem, right? And that was sort of the benchmark. So we're now at a much higher level there. So, but there's going to be work that needs to be done to optimize solvers as we go. We all know that. So, go ahead.
Thanks. I have 2 questions. The first one, you mentioned the gentleman on the right.
Hello?
Far left. Yeah, hello. Version 2.1. So how is the standard the standard committee gonna deal with trying to avoid deprecating language features in the future?
So that's okay.
Legacy.
That's always an issue. I don't think, other than the entire C++ library, I don't really think we've deprecated much, if anything. Right? So yeah, that we're always conscious of that. You know, from 1.1, well, we did 1.0, and then we did 1.0a, I think, and then we had 1.1, right? From 1.1 to 2.0, I don't think we deprecated much, if anything. But at that point, nobody was really using it much, so it wasn't that big a deal. You know, if we tried to deprecate something out of System Verilog today, we'd be crucified, right? So that's not going to happen. I think we're now far enough along, and as somebody who's been doing standards as long as I have, we're always cognizant of the cost of deprecating something. So we really haven't. We have added additional syntax for things like arrays and stuff to allow you to do more stuff, but we still support the old notation if need be. It's just we don't allow you to do everything else that you can do with the new notation, right? That kind of thing. So yeah, it's something we're very cognizant of, and we do our best to minimize.
All right, thank you. And I think the second one is a tool question. There are a lot of, I think it's, as you mentioned, a legacy problem. But from the other side, there are a lot of companies with a lot of C++ running code that maybe one would like to reuse at the IP level. So portability in the other direction. Are there tool efforts ongoing? So this is probably more.
Well, that was the same question before, right? Arbitrary C++ code is not possible to deconstruct to turn back into PSS, right? But if you have C++ functions or whatever that you're using, those can be the realization of a PSS action, right? So there's that way of doing it.
Sure, but I mean, there are companies that maybe have decades worth of development work that they would want to reuse and take advantage of in the maybe at an IP level through some portability, because I guess none of these tools are going to come in cheap. So
I guess there won't be any tool soon, I guess. But you could think of it in terms of value and really evaluate. So let's say you are at SoC or post-silicon and you already have a lot of test content in C++. And those test let's say you have in C. It's easier. And then you want to take that and use it in your IP level environment. You got to choose at what level of IP you want to connect, what level you want to connect your API to your IP simulation environment. So it could be maybe read or write register level. And that you can easily connect to your IP, right? And then at the higher level, you define your PSS model where you think is the value. Well, my model is this, my test attributes are this, and these are the rules, and these are the agents executing that. So that's your model. Now, what is that level where you're calling those bigger APIs or higher level APIs directly from PSS exec body? And it could be, I guess you could directly call the C, and there are ways where you can maybe at the lower level directly connect it to your UVM sequences or whatever. So it's in my mind, it's a value thing and how you want to design it.
Yeah, it sounds like a lot of work.
But let's keep in mind, okay, because we're all getting the same question is being asked: how do I transition? Right? There was a time, actually before my time, that we all drew schematics, right? The Apollo machines were the rage, and Falcon Framework 7 and all these things. And along came some little company that said, we're going to do RTL synthesis. All these questions were present there. Hey, I have all this legacy schematic capture. I'm going to reuse it, right? Oh, if we just implement my hardMac, then I won't be able to remap it to something, blah, 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 right? We brought along synthesis for design, and the world has completely changed, right? We can do things today that we could never do 20 years ago. This august group of people are doing the same thing for you with test content, right? And that is the magnitude of what we're doing over here. But yes, there will be change.
Well said.
Thanks.
Okay.
Good morning. Am I allowed to advertise another session here at DVCon? It's very related to everything that we're talking about.
Yeah.
So,
as long as it's not a product,
it's not a product.
Yeah.
So I'd like to provide some comment and a success story of what I've been working on with Portable Stimulus. So firstly, I've had a lot of fun working with it. And the shameless advertisement is I have a poster tomorrow, and which talks about using portable stimulus in not the traditional way of, let's say, vertically, which is, the smallest unit all the way to SoC, or even, horizontally, which is emulation to simulation. What we've used portable stimulus for is other aspects that we do in our day-to-day life. So there are a few questions in here we talk about, I have this huge validation framework, how do I port it up to PSS, right? But the main problem is people don't know how to measure what they already have, right? And so the first thing is, if you knew what a number was that identified what the quality of your validation collateral was, so if I have 1,000 tests, right? If you could assign a number to that, said the quality of these 1,000 tests is 80%, let's say coverage, right? If you were to write brand new stimulus, like somebody said, you have to put in the work. And if you wrote portable stimulus code, and if you were to achieve that same number, now you know that with the amount of effort that you wrote stuff in portable stimulus, it actually equates to those 1,000 test cases that you had. And that's one of the things that most companies, including mine, lack, which is we don't have proper coverage. So what we did with portable stimulus was we had 3 types of coverage. One is white box coverage, which is traditional, black box, which is also traditional, but we also did something very unique, which is stimulus coverage. And that is how transitions upon transition of actions can actually translate to a test plan, which people don't really look at because they just look at this is my cycle on a bus and how do you up level that, right? And people are worried about that because they write their content looking at bus cycles and not so much the test plan.
Okay.
So that's what.
That's a poster?
It is. Yes.
Okay, great.
And
as poster chair, I encourage you to attend the poster session and check this out. Okay.
And then the other thing is gatekeeper a commonly used term in the industry? So if I said, it's basically a continuous integration system where you say, if I want to turn in my code, I run through this gatekeeper process, which is continuous integration, and I run my same test. One of the problems we faced was most of our tests are UVM, and the whole gatekeeper process is timed. So if you overshoot that time, you get kicked out, and your whole regression, everything just fails, right? So people have come back to us and said, go fix your UVM test bench because it's constrained random, it's seed based, and now you can't fit in the time slot that's allotted. So what we use Portable Stimulus for is to recreate these test cases, which are now static. They are still random, but they are static per seed. And now we could take that from a test suite and just run that. So the benefit we had was to use Portable Stimulus as a reproducibility engine to say, I'm always going to reproduce these same test cases. The benefit we had was, as the project milestone changes, you have that one PSS test, which is static, and you can verify the same feature at every single milestone versus what most people have today, which is a UVM test suite, which may change because the test band changes, the test change, and so on, right? Nice. So that's one aspect of this. And then finally, the cost. So it obviously depends on the tool, but to just give.
Okay, are you giving away your entire poster here, or? Are you...
Sorry, no. I want to just. I'm trying to address somebody what they talked about, right? So I took 2 years to come up with a test plan that gave me 90% coverage, but the tool that we were using was we would get to give you an idea. One cycle test with one cycle took 2 seconds, right? Not bad. A 10,000 cycle test took 27 seconds. Right? Now, those were very simple constraints, but still, the tool gave me something that I didn't write in 27 seconds. And when we used the measurement, which is what I'm talking about, like if you had a tool or if you had a number to say, this is what my quality measures, then if you were to write Portable Stimulus code, however long the effort took to actually write it, now you can measure, and that's your cost. Right. And that's how you can actually quantize the amount of time you take and the value you would bring to your team to move to Portable Stimulus. Right?
Great, so, thank you.
Thanks.
So I have a question about Portable Stimulus being a DSL. Sorry. Yeah.
Domain-specific language, right? Yeah. It's now called PSS, yeah.
And Mike kind of mentioned that one of his pain points was that he just wanted to use a CSV file, right? So, and IOs are supposed to be coming with the new version, right? So, I guess my question is, like, how is that? You need to sell me on why I need to learn another language when there's lots of languages that can read CSV files already, and how this domain-specific language kind of is a benefit, right? I don't want to have a Python script or something else wrapped around this domain-specific language to kind of do all the other things I want to do. That makes sense?
Well, it is a language now. Every language is domain-specific language. It is a full-blown verification language. And the part about reading, writing file is something what we call core library. It's not really part of the language. It's just that you have some functions that you can use to read files, or there will be some other use cases like a lot of math functions that we're going to put in the library.
Right.
And you can actually do that right now through PSS import. You can directly call during solve time C++ functions. So that's kind of a smaller point that we may or may not have some of the library functions that you may need. But you can always talk to the committee, or I guess there's a forum where you can post questions and requesting, and we can add those functions. But the language itself is a full-blown language, and it's have all the capabilities for design verification.
I'm going to argue just a little bit. It's evolving towards a full-blown language, general-purpose programming language. We started by focusing on what's the core value that we wanted PSS to add, and that was really at the declarative level. How can you describe these scenarios at a high level in such a way that tools can map them to really low-level platforms like bare metal software? So we focused declarative first. ever since then, we've been adding in more general programming features. And so more and more today, you're able to do those utility tasks in PSS rather than having to jump out and do those in C and put some sort of language, DPI-like layer between them. Personally, I see that process continuing to the point where you do have a fully fledged general purpose programming language alongside the differentiated, different declarative layer above that.
Right, and the other thing about the CSV, if I may, right, so a lot of times people use that for defining their registers and all that kind of information. We represent that same information in the language, so what you're doing would be reading the CSV file to figure out how to set up your register model in your PSS, and then you have the ability in PSS to use that as a first-class element in the language, as Hillel pointed out. Right, so it's just a way of getting that information from CSV into your PSS model. It's not that you're necessarily processing it in any other way. You're bringing it in as just a shorthand way of specifying the same information that you can then generate for PSS, and then let PSS use that as it generates the scenarios. Okay. Thanks. I just will point out that, as I think I mentioned, because there's so much new functionality here, we will be having a public review period for the new version of the standard. So you'll be able to see it, download it, read it, comment on it, and we'll be able to take your feedback back in as part of the release process. So we look forward to that. All right, last question.
Yeah, I hope.
You're standing between everybody and lunch, so.
Few more minutes only. My question is it's related to PSS in depth. Why do we need explicitly binding? It's already there is a action inferencing in my PSS. So I've already declared my pool and bind of my data flow objects. So why do I need to declare the explicitly to bind?
So
Prabhat, you mentioned that in your presentation.
You don't have to do this, especially on a smaller model, or even for a bigger model where you don't have a lot of constraint complexity. The tool will do the fine job of binding for you. But if you have an IP where you have a lot of constraints, sometimes the constraint solver might not work or take a long time. So, because the binding is done through constraint solving. So if you do that explicitly for some of the action where you kind of know that this is the action that's going to be inferred all the time and this is what I want, it's actually better to just put that in as the action that's used by a next level of actions or your test writers. Maybe you can have another action that doesn't bind, right? That gives you more flexibility.
It's a way of simplifying the problem that you're asking the constraint solver to solve, right? If you know what the binding is going to be, you can put it in. In a lot of cases, going through the pool, there's only one solution anyway. So you might think that you don't have to put it in, but if you put it in, it's just you're not asking the constraint solver to come to the conclusion that there's only one solution, right? So you don't have to, but in some cases...
I don't like any of those answers. To me, the answer is, it's just a simple over-constraint, right? You might have a base model that says you can infer from anywhere, but you might need a scenario where you say, but for this scenario, I need you to get it from this agent.
Mm-hmm. Keep in mind that you have a pool of, specifically for buffer objects, you have a pool of buffer objects. That pool grows and grows and grows. And you want to control your intent. You want to know which buffer object a certain action is going to use, right? If you do a constraint base, you're not going to know. That's why you want the explicit bind as well.
Okay. So, but for that I can define multiple pools. Like if I can make the instances of my pool that it will indicate the number of inputs and outputs to connecting them if I declare the multiple pools, and why I need to specifically to give the external path to look my input into.
Again, you don't need it. In some cases, it can help. It can make things more efficient.
To direct visibility.
But you don't need it. Yeah, if you want to create 1,000 pools and set everything up so that each action can only use one of the pools, go for it. But you don't need to do that, and right, it's a style issue. It's not a technical issue.
Okay.
Okay.
Yeah. Thank you. Yeah.
All right.
Sure.
Thank you, everybody. Thanks for coming.
You.
Welcome back to DVCon, and enjoy the rest of the week.